I'm Paulo, and this is my fourth lab report for Physics 2212. So, to introduce this lab, we do need to discuss a couple of important relevant topics here, and we also need to talk about the purpose. So the purpose of this lab was to analyze circuits with resistors in series and parallel, and also to analyze circuits utilizing capacitors. Now, some of our relevant models and fundamental physics principles here include the node rule, which states that all the current going into a point must equal the magnitude of all the current coming out of the point. Kirchhoff's loop rule, which states that the change in electric potential around any closed loop in a circuit must be equal to zero, and also Ohm's law, which deeply relates electric potential, resistance, and the current at different for resistors. Now, here's a little preview of our final results. We have a little linearized equation here relating the change in electric potential across capacitor over time. We also have one more formula here that I forgot, is the change in electric potential of a capacitor is equal to the charge of the capacitor divided by its capacitance. So for our experimental setup here, we use PHYS virtual circuit construction kit because I was not able to do this experiment physically in person. So for part one, we dealt with charge conservation and energy conservation in series circuits. So the circuit setup here involved setting up a digital circuit with two resistors, two batteries, and wires connecting them in the virtual simulation. Now, our system includes the circuit, which is the resistors, wires, batteries, all that included, and the surroundings is everything else that is not in this circuit. The initial conditions is this circuit here, but without the ammeter, so just the wires, resistors, and batteries, and the current is flowing through it constantly. Now, when it comes to some of the math stuff here, there were a couple of slight discrepancies, but they were on the order of magnitude of like 10 to the negative 3, 10 to the negative 4, and this is probably just due to some rounding errors because we're dealing with idealized situations here, which should follow idealized math. Now, the first thing that we had to do here was calculate the current in the wire, and I actually argued that since there are no nodes, the current is constant throughout, so I used that with the loop rule around this main loop here, and ended up with the theoretical value of 0.0204 amps. And when I connected up the ammeter, I see that it's 0.02 at every single point in the circuit. So my theoretical calculation matches the measured. And when I used my voltmeter at locations before and after the batteries, for some reason I got 3 volts positive on both sides. I'm not sure why that is, and we'll get into why later. Now also reversing the ammeter also got me the same current magnitude and direction, 0.02 amps, which is also a little weird. The next thing we had to do was measure the change in electric potential between several points. For example, one part of the battery up to a resistor in between the two resistors, and so on, yada, yada, yada. And the whole point was that when I measured up these changes in electric potential, I actually ended up with net zero electric potential, which follows Kirchhoff's loop rule that should be the case. Now, why doesn't the ampere reading change when the voltmeter is connected? This is because in an idealized situation, the voltmeter and amperes, or ammeters, do not have any significant resistance. So the current should not decrease due to these. Now, also, when I added an ammeter that was parallel here to the resistor, so connecting this point up to like here on the wire, all the current jumped up to 0.06 throughout the entire thing, and that's probably due to there being a node that we had to account for now. Now, I went ahead and graphed the change in electric potential throughout the circuit as a position of the circuit. So as you go through the batteries, you gain your 3 volts of electric potential. Go through your first resistor, lose a little bit because it doesn't have as much resistance as the second one. And then the second one, you lose way more all the way down to 0. So that way you have 0 change in electric potential throughout the whole thing. So that's that. That's the first part of the lab. Oh, we also had to calculate the resistances of our resistors theoretically based on our change in electric potential. And I ended up getting the same results back. This used Ohm's law. So I used delta V is equal to R is delta V over I, and I ended up getting 47 ohms for the 47 ohm resistor and 100 ohms for the 100 ohm resistor. So for part 2, I analyzed an RC circuit, and the circuit system here is this: battery, light bulb, which is our resistor, and our capacitor. And this is our system, our surroundings is everything else. Our initial condition was this without the voltmeter here and without a charge capacitor. So the first thing we had to do here for this part of the lab actually was to just see how the light bulb would react to charging and discharging the capacitor. Now, the light bulb, when charging the capacitor, would be bright and then slowly dim as the capacitor gains charge because it gains resistance due to the capacitance formula. Now, when I was discharging the capacitor, same thing happened. The light bulb started bright and then dimmed down because the current was now going the other way as the thing discharged. So now, I also measured the charge and discharge times of the capacitor, and it was 6 seconds for 10 ohms and about 10 seconds for 20 ohms, both for charge and discharge. Now, the last thing we had to do here was actually calculate the time constant for this capacitor, which is 1 over the quantity resistance of the resistor times capacitance, which is 1/6 what I got. Or I got 1/6. And then when I graphed the linearized data here using a formula we were given, which is actually the natural log of the change of potential across the capacitor divided by the initial capacitance, or initial electric potential, is equal to negative time all times 1 over RC. So it's linear, and the slope was that. So now, over here, conclusions. So the first what-if question, there would be less than the expected resistance in the wires because the ammeter would actually have a bit of resistance and it would act as a resistor. So the current would be lower than expected. And if we didn't have any kind of resistor for the RC circuit, what would happen is that the capacitor would not charge instantly as it does in the simulator because there would be a little bit of resistance in the wire. So it would take actually some time. But